Hello again. Today we want to talk about linear homogeneous equations with constant coefficients that have a characteristic polynomial with some complex conjugate roots. Now, last week I gave you an example of how to solve such a problem, but we didn't go into the theory behind exactly where that solution came from. So today I want to spend a little more time talking about theory here. So as an example, we might think about an equation that looks like y double prime plus 4y equal 0. So that's homogeneous. It is second order, but it is a linear differential equation. And so if we were confronted with that, I think the first thing we would do would be to find the characteristic polynomial. And that would be r squared plus 4 equals 0, which would have a solution or solutions. R is equal to plus and minus 2i. So complex roots for polynomials always come in conjugate pairs. 2i and minus 2i are a conjugate pair. If one of them is a root, then the other will be also. So we always get those in pairs. Now that we've got these two, we could observe that y1 equal e to the 2i is a solution to the differential equation. You could try that and see. And y2 equal e to the minus 2i is a second solution, and they're linearly independent. I guess I probably should put an x in here, huh? And they're linearly independent solutions. Now, the problem with that is that they're still complex, and we'd really like to have real valued solutions. And so what follows next will bring us to a point where we have real valued solutions, even if the characteristic polynomial has some complex roots. And so we want to recall, and I don't remember which class you recall this from. You may recall this from Calculus 3. I don't remember where you picked this up. In fact, if this is the first time you've seen this, that's fine also. There's something called Euler's formula. And Euler's formula just says that e to the I theta is equal to cosine theta plus I sine theta. And that's Euler's formula. So from that, what can we figure out here? Well, we'll come back and finish solving this particular problem, but let's be a little more general right now. Suppose that we have a complex root z equal a plus ib. Now that's exactly what we have in the problem that we're working with the exception or the stipulation that a, in our example, that a is 0. And when we're dealing with complex numbers, the part without the I is called the real part, and the part with the coefficient I is called the imaginary part. So this would be real part, imaginary part. In this example, real part is 0. But that doesn't change how we're going to proceed. So that's just an artifact of the example that I picked here. So suppose that z is equal to a plus ib, and z would be, in our supposition here, z would be a root of the characteristic polynomial. So a solution would be y equal e to the a plus ib x. And I think I'll just call that y1. And that would be further equal to e to the ax e to the ibx would be e to the ax, and now using Euler's formula, this would be cosine bx plus I sine bx. And we call that y1. Now, if a plus ib is a root of the characteristic polynomial, then a minus ib is also a root. And so without belaboring this, we could say that y2 equal e to the ax cosine bx minus I sine bx would be a second root, and we could get a general solution as y equal c1 e to the ax cosine bx plus I sine bx plus c2 e to the ax cosine bx minus I sine bx equals, and I'm going to jump ahead and let you do some of this algebra just to verify what we've written there. But I think you will be able to see easy enough that we can wind up at, just by factoring here, this would be an e that I intended to write here. See, we've got an e to the ax and an e to the ax, and so if we factor that out, we could write this as an e to the ax, and then let's make a square bracket, c1 plus c2 cosine bx plus I c1 minus c2 sine bx, and close the square bracket. And that would be for arbitrary constants c1 and c2. Arbitrary constants, and that would be real or complex. They're arbitrary constants, but they can be real numbers or they can be complex numbers. And that's a general solution, but what is unsatisfying about it is it still is complex. It still involves the I. But now here's something for us to note. The C1, C2 can be any arbitrary constants, real or complex. And so if we would let C1 equal C2 equal 1/2, then we would have a solution. And I guess I'll call this y1, because I'm going to get a second solution for us here in just a minute. We would have a solution that would look like what? C1 equals C2 equal 1/2, and so it's an e to the ax. This would be 1. This would be cosine bx. C1 minus C2 would be a 0. So this would just be e to the a x cosine bx. That would be a solution to the original differential equation. And we could say also, that's not the way you spell also. We could let C1 equal negative I by 2, and C2 could be positive I by 2. And then we could form a solution y2 equals, now we're substituting here again, C1 is negative I by 2 and positive I by 2. So these are going to add out. And so I'm going to have an e to the ax out there in front, of course, e to the ax. But this is going to be 0. And what am I going to have here? I'm going to have negative I by 2. Just work inside the parentheses. Negative I by 2 minus I by 2. So this is going to be a negative I. And then I've already got an I out here. So I times negative I would be negative I squared. I squared is negative 1. Negative I squared is positive 1. So sine bx is what I have left. So again, I know if I have the complex conjugate pair a plus ib, a minus ib, then I'll have solutions y1 equals e ax cosine bx. That's going to be a real valued solution, but it is a solution. And y2 is e to the ax sine bx. We could use the Wronskian to convince ourselves, if we're not already convinced, that these are going to be linearly independent solutions to our constant coefficient linear differential equation. If they're linearly independent solutions, they form what's called a fundamental set, in this case a fundamental pair, and so I know that any solution y can be written as e to the ax c1 cosine bx plus c2 sine bx, where c1 and c2 are arbitrary constants. Any solution y can be written in this form. And, well, here's why we have gone through this process, because notice that I've now got a general solution that doesn't involve I. That is, it's a real general solution. So that's what we do with complex conjugate pairs. Now, in the example we've been working, we've got a root z equal 2i, and so a solution, well, let's say z equal 2i, we know that these come in conjugate pairs, so maybe we'll even call that one z1 and z2, and this would be negative 2i. And so following what we've done above, our general solution is going to be y is equal to e to the ax. Well, a is 0 in this complex number, and it's 0 in that complex number, so it's going to be a 0x. You're saying I didn't have to write that, and you're right, of course I didn't. Cosine 2x plus c2 sine 2x, And that is why, since e to the 0x is 1, e to the 0 is 1, this would just be, in our case here, c2 cosine 2x plus, I don't know why I wrote c2, c1 cosine 2x plus c2 sine 2x. And that gives us a general solution to the differential equation y double prime plus, forgotten what the equation we were solving was, plus y, plus 4y equals 0. So that's pretty nice. Now, maybe just another thought. This isn't too long. I know you've covered this in your readings, but what if a third order linear differential equation homogeneous has characteristic polynomial with roots R1 equal 2 plus 3i, R2 equal 2 minus 3i, R3 equal 5. Okay, now let's review a minute. The third order, we're speculating here, what if a third order linear differential equation, homogeneous, well, you know, if it's not homogeneous, the associated homogeneous equation would be an example of what we're talking about here. So this is a useful thing to think about, whether the equation in front of us is homogeneous or not. If it's not homogeneous, then we're going to have to solve the associated homogeneous equation to get a general solution anyway. So this should be interesting stuff. What if it has characteristic polynomial? Now it's third order, so the characteristic polynomial will be of degree 3. If it has one complex root, then the conjugate will also be a complex root. So I have to have a pair of these. If I'm going to have one, I've got to have a pair. And then somewhere in the complex numbers, any third degree equation, third degree polynomial, has 3 roots. And so suppose the other one was R3 just equal to 5. Then we could say a solution will be, and this is all I'm trying to impart to you or share with you right now, is that we would use these roots and what we have already done, but you just keep adding on terms to the solution depending upon how many roots you have, like this would be y equal e to the 2x c1 cosine 3x plus c2 sine 3x plus, now you see this term takes care of the complex conjugates. They've both been used here, plus e to the 5x, and we're done. Well, We're almost done. C3. If it's a third order linear differential equation, we know the general solution will have three arbitrary constants, C1, C2, and C3, as you see right there. So we would just, you would just add terms. And what if it was, you know, still got some paper left, and I feel like we got a little bit of time left. What if we had a characteristic polynomial with roots R1 equal 2 plus 3i, R2 equal 2 minus 3i, R3 equal 5, and R4 maybe is a repeated root, a repeat of R3. So 5 may be a repeated root. Then since I've got 4 roots here, the characteristic polynomial must have been degree 4, which means that the differential equation must have been order 4, and the general solution is going to be y equal e to the 2x cosine 3x plus sine 3x. Now I forgot the constants, so I'm going to put a C1 in here and a C2 there, plus C3 e to the 5x plus, and then as you know from problems we worked together and from reading your book, the repeated roots 5 and 5 would give rise to terms e to the 5x and x e to the 5x. So if a characteristic polynomial has these 4 roots, then this is what the general solution would look like. And you can extrapolate from there and figure out what other solutions would look like. But, you know, that's it. You've got a characteristic polynomial, and you find the roots. That's an algebraic problem. May not be terribly easy, but it's easier than differential equations. And from those roots, you can build a general solution. So we're talking about linear differential equations, typically of any order. The ones we usually solve are order 2 or 3 or 4. It's sort of unusual to go higher than that, but it would work just fine. And the characteristic polynomial will find the zeros or the roots, and they're going to be unique real numbers or duplicated, and the multiplicity can be anything. It doesn't have to be 2. So they'd be real distinct roots, real repeated roots, or complex conjugates. And to form the general solution using addition, we just keep piling on terms that correspond to those roots. So I hope you understand all this, and have a good afternoon or evening or night or whatever. Thank you.